Today we'll be talking about linked lists, so let's jump right in. Linked lists are a data structure that is characterized by a few different things. First thing, every linked list has a reference to the head node, which is the first node in the list. Also, nodes in linked lists contain some type of data and also reference to the next node in the list. These types of lists are called singly linked. There's another type of list called a doubly linked list. And in doubly linked lists, in addition to the next node reference, we also have references to the previous node in the list. Note that in a linked list, the last element will have a next node reference to null. And in a doubly linked list, the first node will have a previous node reference to null as well. Remember that in interviews, it's really important to ask clarifying questions. A lot of times when you get linked list questions, it can be important to clarify exactly what kind of linked list you're dealing with. So just keep in mind that there are different types of linked lists, and ways we can categorize them include thinking about whether they're singly or doubly linked, also thinking about whether they're sorted or unsorted in terms of the order of the data, and also some linked lists can have a tail reference, which can be useful for some problems. So now let's talk about some of the time complexities associated with performing different functions with linked lists. So here we'll be talking about unsorted linked lists, unless I mention otherwise, so just keep that in mind. So whether we have a singly or doubly linked list, how long does it take to access a specific element? It takes O of n time, in the worst case. The reason for this is, it might be the case that you have, you're actually trying to access the last element in the list, so you'll have to traverse the entire list to get to that element. Now you might be thinking, well, what if I have a head and a tail reference? Then I could, really easily get to the last element in the list. In that case, then the hardest element to get to would be the one that is right in the middle. And to get to that element, you'd still have to traverse half of the list. And this is still on the order of n elements. Note that this is differentiated from an array. In arrays, you can have O of 1 access to any element in the list, regardless of its position in the list. Now let's talk about searching. How long does it take to search for a specific element in a singly or doubly linked list? Turns out this also takes O of n time for much the same reason that I talked about just a second ago. It might be that you're searching for the element that shows up last in the list, and so you'll have to traverse the entire list to get to that element. As far as insertion, how long does it take to insert an element into an unsorted singly or doubly linked list? It takes O of 1 time because you just can add it right to the beginning if you have a head reference, and you could also add it to the end if you have a tail reference. That way you don't have to traverse the list to insert, and it takes constant time. Note that if the linked list is actually sorted, then you will have to traverse the list to find the right position at which to insert the element. So with sorted linked lists, insertion would take O of n time. Now let's talk about deletion. How long does it take to delete an element from a singly or doubly linked list? Now, we know that when we actually delete something, we're going to have to search for it first. So let's kind of remove the searching aspect of deletion from our thinking right now, and just think about how, once we know where an element is, how long does it take to delete that element? Turns out it takes O of 1 space, because once you have a handle on exactly where it is in the list, you can just change the previous element's pointers to point not to that current element, but to the thing that's after it in the list. So this function takes O of 1 time. Again, just note that this is after we've already found the element that we want to delete. So now, some tips for solving linked list problems. Really, the most important thing to remember is that you can use a lot of the tips that you use to solve array problems for linked lists. So for example, FastI SlowJ is still a really useful technique to keep in mind when you're trying to solve linked list problems. And actually right now we'll take a look at one problem that you can solve using FastI SlowJ for linked lists. Let's say you want to find whether a linked list has a cycle in it, meaning that there are elements in the linked list, at least one, that point to a previous element in the linked list. And so if you start just traversing the linked list, in fact, you'll stay in that loop forever. How could we find whether this is the case? One way to do this is using FastI SlowJ. So let's say that you have a J pointer that you move, that you use to step through the linked list and iterate through it. And let's say that at every step in this algorithm, you move forward 1. And now let's say you also have a I pointer, which will be the quote-unquote faster pointer, and for every step in the algorithm, you move two nodes forward in the array. In fact, if you keep doing this, you will end up in a situation where the I pointer and the J pointer are pointing to the same node, if there is a cycle in the linked list. If there's not a cycle, then very soon you'll get to the end of the linked list. The I pointer will get to the end of the linked list and you'll realize, oh, there's no cycle. But if there is a cycle, before you get to the quote-unquote end of the list, which actually this one does not exist, you'll find that your I and J pointers are pointing to the exact same element. And then you'll know that this linked list has a cycle. So this is just one algorithm for finding a linked list in a cycle, and there are others, but this is, I thought, pretty cool because it uses the same FastI SlowJ technique that we've been using to solve other problems earlier in the class.